I hope you can all see it.
Yes, we can
Pauline,
see
is it
your
visible?
screen.
Yes.
Okay, thank you so much. Part of what I'm going to be presenting is some of the results that I've obtained as I've been working on my PhD. So I really welcome any suggestions and comments as I'm preparing for my defense soon. So thank you. Currently working as a tutorial fellow at Kibabi University, awaiting my graduation. And I'm going to be giving a talk on the enumeration of non-decreasing, or I can call them weakly increasing, two non-crossing trees. So allow me to begin this. I'll try to make it understandable to a layman's. I'm really going to try my best. My presentation lies under the area of graphs and trees. So I'll just start with a basic introduction. A graph is something that we have all been working with ever since we started studying maths. It's something that we are familiar with. It's a structure that's mainly comprised of vertices and edges. And under graphs, there are various types of graphs. And this research falls under simple graphs. And simple graphs are graphs that have no loops. That is, you do not have an edge from a vertex to itself, and we also have no multiple edges. In between any two vertices, we only have one edge. And when such a simple graph has no cycles, then we obtain the structure that is called a tree in combinatorics. I've provided an example where we have two structures. The one on the left is an example of a non-tree, because there is a cycle. You can see between vertex 1, 2, 5, and 6, you can go around in form of, say, a circle. So that disqualifies this from being a tree. But in the second structure, moving from one vertex to another, there is only one single path that you can use. So that makes it a tree. And under trees, there are various categories of trees. We have plain trees. These are the most common trees, if I'm to call them that have been studied. They have been studied for quite so long, back into the 1980s. There was a research that was done on the enumerating formula for the plain trees, they were found to be enumerated by the generalized Catalan numbers. Catalan numbers, for those in combinatorics and even those not in, these are famous maths numbers that are used to enumerate quite a number of structures. Another category of trees, we have the non-crossing trees. This is where my research falls under. And then we also have tree-like structures. These are structures that are not trees, but they borrow properties from trees, so such as Husimi graphs and so on and so forth. So I'll concentrate on the non-crossing trees. And by definition, these are trees whose vertices lie along the circumference of a circle. I've given an example in form of a structure. This is a tree where all the vertices, they can be combined. If you draw a line, you get a circle around them. So this is an example of a non-crossing tree on 7 vertices. In this talk, I'm going to be labeling my vertices in an anti-clockwise direction, but you can also do it clockwise, depends with what you're comfortable with. Now, the research on enumerating these non-crossing trees was done, if I'm not wrong, it should have been by Noe, who found that these non-crossing trees on n edges or on n+1 vertices are also enumerated by the generalized Catalan number, as I've given the formula back there. Under the non-crossing trees, we can put in a condition to get a subset, which gives us the k non-crossing trees. Now, in this case, consider the same non-crossing tree that I described, but now we are going to assign labels to our vertices, and our labels are going to come from the set numbered 1 up to k with a specific condition, and that condition says if you have an ascent, that is, if you're moving from a lower vertex to an upper vertex, that is an ascent. If you add the labels of those two vertices, the sum should not be more than k+1. Let's look at this example here. From vertex 1 to 2, it's an ascent. And as you can see, what I've put in subscripts, they are values 1 up to 4. So in this case, this is a 4 non-crossing tree. And when we look at the edges that are ascending, for example, 1 to 2, it's an ascent. If you add 3 plus 2, you get 5. That's at least k plus 1. 2 to 3 is also an ascent. 2 plus 2 is get 4. So that satisfies that property. But if you look at 8 to 7, we are not ascending, we are descending. So 4 plus 3, the value gives us 7, which is, of course, more than the 5 that we need in this case. But that should not interfere with our structure because the condition is strictly working on the ascents. So the k non-crossing trees falls under what I am going to be giving a talk today. I'm just giving a brief general background so that we can all be on the same page. So this is an example of a 4 non-crossing tree. Again, I've labeled the vertices in an anti-clockwise direction, and it has 8 vertices. Now, there is a method that was introduced by Prondinger et al. In 2002 in enumerating of non-crossing trees. When you're enumerating these trees, the ones whose vertices lie along the circumference of a circle, it's a bit complicated to be able to get how many trees of this number of vertices there exist. And while it is easier to enumerate them as plane trees. So they introduced a method called the LR representation, which I'm going to be borrowing for this talk, where you just pull out this tree from within the circle. And of course, like here, we have a vertex 1. This vertex is going to be at the most top here, and we call this vertex the root. And then the vertices that are going to be attached, we have 4 and 6, we pull them out here. And we label them in such a way that if we are ascending again 1 to 4, we are going to label the ascents R. For example, 1 to 4, we are ascending, so we label that vertex R. If I move from 4 to 3, we are descending, so I'll label that vertex L. 4 to 2, it's a descent, also we label R. So we get such a tree, and this tree is ordered, meaning it's a plane tree. And while we are looking at these trees, there are some terms that I'll use. I'd like to just say them out to at least have us move together. The vertex at the most top on trees, this will be referring to that as a root. These are common terms that are used. And these vertices at the center, they are internal vertices. And if such vertices are not having any other subjects from them, we call them the leaves. And all these vertices that are sharing an origin, we consider the case of a household. You're sharing a parent, so you're called siblings. I'll be calling them siblings. So R is a parent to L, L and R, and these 3 are siblings. Those are such terms I'm going to use. So we are going to apply and borrow this method of representing the k non-crossing tree into plane trees to make the enumeration of our trees easier. So by use of the LR representation, which now brings me to the set that the trees that I am giving a talk on. We call them the non-decreasing 2 non-crossing trees. Non-decreasing can also be referred to as weakly increasing, meaning these trees, once we get the LR representation from the non-crossing tree, when we get the plane tree, there is an order in which we are going to be labeling the L's and the R's. So we are going to have, first of all, it's a 2 non-crossing tree, meaning all our vertices are either going to be labeled 1 or 2. You can consider this in terms of a binary representation where we have 0s and 1s. It's a bit easier to understand that way. And all the R's and the L's, they are going to appear in an order where 1s appear on the left of 2s, and all the L's will also be appearing on the left of R's. So for example, in this case, this is a 2 non-crossing tree. As you can see, all the subscripts are either 1 or 2. These are the labels of our vertices. There are 7 of them. I pull that into the plane tree using the LR representation. I get this representation without changing the label of the root. And then, as you can see, the first one, root has two children, R1, R2. R1 represents vertex 4 with label 1. R2 represents vertex 6 with label 2. And then R1, which is our 4, it has three children, which have labeled L1, L2, R1. So our L1 is this 2, 1, because we are decreasing from 4 to 2. L2 is this vertex 3, 2. We are decreasing, so it's L, and then we are carrying that label 2 there. And then 4 to 5, we are increasing, so it will be R, and 5 has label 1, so we carry 1. That's the aspect that we are going to use it as we are representing our non-decreasing to non-crossing trees. In enumerating these trees, I also borrowed the methodology of butterfly decomposition. This was very much introduced by Flagellate and Noy in the enumeration of the non-crossing trees. As the name says, butterfly, we are borrowing the concept of a butterfly. A butterfly has two wings, one on the left and another one on the right. So if we consider, let me go back. If you consider this LR representation of our trees, since some of them are labeled L and some of them are labeled 1R, sorry. So in our butterflies, the left wing is going to contain non-crossing trees with L's, and the one on the right is going to contain non-crossing trees with R's. So we are going to decompose a non-crossing tree into butterflies, and then we apply the method of generating functions to be able to obtain the enumeration formula. Remember, that's our main goal of this research. So if the root has degree D, or in simple terms, if it has D children, then we are going to get D such butterflies. So having this in mind, I'm able to introduce the concept of the generating functions. I'll go back to explain. So N of X will be representing the generating function of the non-crossing tree, and B of X will be representing the generating function of the butterfly. So back to our structure, let's start with the non-crossing tree. We'll have X marking a vertex. So since the entire of this structure is a non-crossing tree, we have vertex V here, so we represent it with X, followed by a sequence of D butterflies. And by applying the Taylor expansion, you remember if you have a sequence, then that just gives us 1 over 1 minus A. But in this case, our butterflies, we are representing them as B. So the generating function of the tree will be X, the vertex, plus 1 over, times 1 over 1 minus B of X, where B of X is a generating function for the butterfly. And next, the butterfly itself, which is this here, we have a left wing and a right wing. And since the left wing is a non-crossing tree, this is N of X. Right, we have another non-crossing tree, another N of X. And both of them are sharing this center part here. So to avoid overcounting the number of vertices, we are going to divide by X because we have a shared vertex there. So we get the generating function of the non-crossing tree now. It will be N of X squared because we have the right and the left over X, as I've explained, to avoid overcounting. So from there, if I get equation 2 and equation 1, and automatically equation 3 just comes in if I substitute this value of B of X here and just simplify, I get equation 3. So we are going to use these generating functions and now apply them specifically to our non-decreasing to non-crossing trees, which is where we are with this slide. We enumerated these trees by taking care of considering the number of vertices that are labeled 2. That is why we are using the bivariate generation functions, where we have X just marking a normal vertex, but specifically any vertex that is labeled 2, we mark that with variable U. So again, we consider this or subdivide this into 2. Remember, we are doing two non-crossing. So our vertices are either labeled 1 or 2. So in such case, we do in two categories. The first category, when the label of the root is 2, we have that generating function to be C of xu. And the second category to be when the label of the root is 1. And remember the condition that we put for the k non-crossing trees. If you're ascending, the sum of the vertices labels should not exceed k plus 1. In this case, since when the root is labeled 2, 2 plus 1 is 3. And it's a two non-crossing tree. So the sum of the vertices that are adjoint to each other should not exceed 3. So automatically that means if the root is labeled 2, all the children of 2 are going to be labeled 1. So we are going to have the generating function.
When you put a video.
We have a vertex x, which is the root. And since that root is labeled 2, we have u. And then followed by a sequence of children, all of them labeled 1. So we'll be having butterflies left and right 1, which is in the generating function of those labeled 1 is d. So we have d squared over x here. Remember, over x is to avoid repeating, as I explained earlier. And when we come to those that have root labeled 1, we have a root, a sequence of those labeled 1s, followed by a sequence of those labeled 2. Because if we have 1, we can either have 1 to 1 or 1 followed by 2. So we have equation 4 and equation 5. Which brings us to the application of the famous Lagrange inversion formula. This is a formula that is used in the extracting of the coefficients from generating functions. Because if you have just this sequence, 4 and 5, it's very hard to find the figures from this without simplifying it. So this is a standard formula. I've highlighted it in blue. It's standard in combinatorics. But first, the first step you do is express our generating function t of x in this case in terms of x times a function of that t of x. So this was the next step. And after some quite tasking manipulation, I found that the only way we could have done that using our formula is to let our c to be the value xu 1 plus y. I introduced a variable y. This will help us with the manipulation. So from our original equation of the value of c, if I substitute this, I'm able to get the value of d squared, which is xy over 1 plus y. That's equation 6. Most of these are just coming from calculations that I've not put in here, but if someone might be interested in learning the calculations later, I will be more than happy to share that. So substituting 6 to 5 and doing further manipulation, I finally got equation 8. As you can see, equation 8, we're expressing d in terms of this variable y that we have here. And further substitution of 8 into 6, now we get a function y, which is x times another function of y, the format that we needed to apply the Lagrange inversion formula. So recall this was the value of c, xu 1 plus y. So if I'm going to look for the coefficients of trees with n vertices such that k of those vertices are labeled 2, it's the same as looking for trees with n minus 1 vertices such that k minus 1 of those are labeled 2. So that applying the Lagrange inversion formula and obtaining the binomial coefficients, I was able to obtain equation 10. So this becomes the formula that enumerates the non-decreasing two non-crossing trees on n vertices where the root is labeled 2, and this k such vertices are going to be labeled 1. This is a formula for C. So I did the same approach now to obtain those from D. Something very similar, expressed in terms of the value of D, which is 1 plus uxy. Apply the Lagrange inversion formula. I was able to obtain equation 11. And since D represents the trees which have root 1, C represents the trees which have root 2. if all you care about is the total, you don't want to know whether these trees have root labeled 1 or these ones have root labeled 2, you can just sum equation 10 and 11 to obtain equation 12. And if you want to go a step further and only find out only the number of non-decreasing to non-crossing trees without caring about this k, you can just sum over k and get that final formula. So from there, I went ahead and looked at a further categorization of the non-decreasing, non-crossing trees. Okoth introduced a category of trees called K non-crossing increasing trees. These are just such non-crossing trees, but then now we only care about the R's without the L's. Remember, in our butterfly decomposition, we had L's and R's. So assume you get rid of the left side of the butterfly, from the structure that I've indicated there. So we are only going to be left with the right wing, only the increasing or ascents from the root. So this, applying it to our non-decreasing to non-crossing trees, we get this new structure. And I went ahead and followed the same approach to perform their enumeration. Now, the same approach, but instead of using C and D just to differentiate, this time I used I and J, but the manipulation and the calculation is more or less the same. But since we only have one wing, the right one, we are not going to have squared here. And here, as you can see, we only have one variable instead of two. So again, I still used the value x, u1 plus y, did further manipulation, and I've not shown the calculations, I've just given the results. I was able to obtain the number of those trees, these increasing ones now, when the root is labeled 2 and when the root is labeled 1, equation 17. And also, if you just sum without caring about how many of those are labeled 2, that is, or if you put the value of u to be 1, you get these three formulas. Up to there, I've just enumerated the trees according to number of vertices. But there are other ways in which you can enumerate trees. You can enumerate trees based on other parameters. Like this is enumerating them by the label of the leftmost child. And remember, when the root is labeled 2, all the children are labeled 1. So you'll not get any different result. It will just be the same result. But when the root is labeled 1, we'll first have the children labeled 1, followed by children labeled 2. And that means we are going to get this generating function, perform the Lagrange inversion formula, and we'll be able to obtain equation 21. Or you can also go and enumerate according to a different parameter, that is root degree. How many degrees of how many such non-crossing are originating from the root. So in this case, I enumerate with root labeled 1 first. If the root is labeled 1, we can have P of those children to be labeled 1 and Q to be labeled 2. That means in total, the tree is going to have P plus Q children. So in getting the generating function, we'll have the root, P of those labeled 1, and Q of those labeled 2. You just do the same, apply the Lagrange inversion formula, and you obtain the result, which is the result 22. When you have the root labeled 2, that means all the children are labeled 1. So the value of Q will be 0 here. So we are just going to have X and JX of P, meaning the root will have degree P. Again, do the same manipulation and obtain equation 23. And this is a third parameter by the number of forests. Again, I am summarizing this. They have more detailed results on this for anyone who might be interested in getting them. So for the number of forests, we consider the real life situation. A forest is made up of a lot of trees. So we are going to borrow the same concept and bring it here. We are going to divide our trees into components, and then these components, as long as they do not intersect each other and they are rooted at the vertex with the smallest label, we are going to be able to enumerate them also. So again, I did that according to the number of forests, and I obtained equation 24, which I can see my time is almost running up, but I'm almost concluding. Allow me to just mention something small on the bijections. I think I've come to learn that in combinatorics, the use of bijections is a very strong methodology in obtaining how many different structures can be counted by the same formula. So I managed to be able to construct a bijection between these trees, the non-decreasing to non-crossing trees, with another set of trees that were introduced and done by Okoth in 2015, the locally oriented trees. So locally oriented trees, just assume this LR representation, it's oriented, meaning there are arrows directing. Where does this edge go? Is it from R1 to R2 or from R2 to R1? And when we have all vertices pointing towards a certain vertex, all arrows pointing towards a certain vertex, we call it a sink. If we have all arrows pointing away from a certain vertex, we call it a source. So and a vertex that is not a sink, not a source, we just call it a non-source or a non-sink, just that. So I managed to find a way to move from our non-decreasing to non-crossing trees to the locally oriented trees and back. So I was able to create a one-to-one mapping and an on-to mapping, hence created a bijection, meaning that these two sets of trees are enumerated using the same formula. I'll just briefly take you through it. So the first step, of course, is obtaining the LR representation, which we've already at least gotten familiar with as of now. And from that, we are traversing our tree in pre-order traversal, meaning in simple terms, we are going to be working from left as we are moving to the right. And our point of interest are going to be non-root, non-source that are either labeled L2 or R2. So in this case, the first one that we come across is this one right here, L2. So you look at its children. The children that are labeled R, you cut them and bring them to the immediate left here. They become siblings. So I have shown that in red here. So they were down here, I've cut and bring them up here and change them from R to L. And then, allow me to go back. These children, the remaining ones here that were labeled L, I change the direction of the arrows and I relabel the L's to R's. So I've changed, highlighted it in blue and changed from L's to R. And then from there, I keep traversing again until I find the next either L2 or R2 that is not a source and not a sink. So it cannot be this. I just keep moving until I come across it. Here it is. We have the vertex R2. So from here, if you have R to R, you cut it and bring it here as a sibling of R2. But this time around, you do not change the label. So I have cut it and brought it here, highlighted it in red. So this R1 that was here, we bring it up here to become a sibling on the immediate right. I keep maneuvering since we are not yet at the end. There is an L2 here. We do the same thing that we did to the L2 originally back here. So we have a child labeled R, cut it, bring it up here to be the sibling and change from R to L. So cut it, it's here, change from R to L, change the sign of the arrow, the direction. And then the remaining L's did the same thing we did in blue. So we are going to change the direction of the arrows and relabel those as R's. And if now I just get rid of the colors, the reds and the blues, this is a final tree that we have. And this is a locally oriented non-crossing tree. So, and vice versa, we can be able to maneuver back to obtain our original tree. So through the algorithm that I created for transforming these, create a bijection mapping, that means these two sets, the set of locally oriented non-crossing trees and the set of non-decreasing to non-crossing trees are counted by the same formula, which is a good result that I obtained there. And I believe I would like to talk about how they are applied in theoretical application, because I know I've been talking about trees and trees, but these are some of the areas that these trees can be applied in. We have a famous application in computer science in the graph theory applications. Specifically, since these trees are labeled 1 or 2, and then there's the aspect of non-decreasing, meaning there is an order. Ones comes before the two. So we consider this in the binary case. Instead of twos, we have zeros and ones. So it can be used in network designs or analysis. Can also be applied in the study of phylogenetic trees, that is study of DNA, ancestral lines, and evolution, that is in bioinformatics. In physics, they can have an application in statistical mechanics, and also in chemistry in the molecular structure representation, studying about the molecular bonds. So there are some of the references that really impacted this work. And at the end of it, I would like to acknowledge the financial funding and opportunities to attend workshops that I received from DAD and the input from my main supervisor, Dr. Isaac Owino. And from this side of Africa, we say asante to mean thank you. Thank you so much.
Thank you, Yvonne, for your nice presentation. We are very happy that you used your time effectively and gave us a very nice presentation. So now it is time for questions, comments, and suggestions from everyone in the room.